The process of assembling modules and setting the detector blocks in place was performed routinely. But in the beginning, it sure took a lot of thought to plan it all out. For instance, plans for the neutrino detector's size were limited to the parts that would fit in a truck. That's why the modules are 52 feet long. Once on site, then comes the task of assembling the 52-foot-long modules. Each module gets hoisted over to the gluing machine. Once on the gluing machine, the module is rotated bottom side up. Then the glue is applied. The module is rotated back to top side up. The glued module is hoisted off of the machine and lowered onto the assembly area, where it is pressed into place. The assembly area is really the top of a giant pivoter on wheels. When 12 modules have been placed edge to edge, one complete layer is finished, and the module orientation in each successive layer is 90 degrees to the previous layer. When 32 layers are stacked and glued, then one complete block is ready to be tilted upright and transported by the pivoter to take its place at the end of the detector. Now comes the part when Mr. Miller took me down to the detector floor. When I stepped out onto that floor, suddenly I felt very small. I also felt like I had walked onto the set of a Star Wars movie. The pivoter was like a giant mobile weapon of the Galactic Empire that could shoot laser beams down on its victims. But as we had just learned, the upper platform was where the detector modules were assembled. The pivoter was now ready to transport the block down a set of tracks, tilt the platform that's carrying the block, and set the block up against the previous block. Once the 28th and final detector block was placed, there was no more need to return the pivoter to its starting position. Instead, it was simply left at the end of the detector as, so to speak, a permanent bookend. Once the detector blocks were in place, they got filled with an oil that's needed in the neutrino detection process.
So this allows us to get out over the detector for filling, and this is the fill cart you see right here. As I mentioned once already, we're almost to the magical 2 million gallon part. So right now there's nobody out here working because they just emptied one of the tankers. There are about 6,600 gallons in each tanker. And now this time of the year, we actually have to heat the oil in the tankers to make sure that the oil we put in the modules is the same air temperature as the building, so you don't have a lot of expansion and contraction when you fill it up.
Another task was to outfit the detector with instrumentation that would signal a neutrino event. And the key component is called an APD, avalanche photodiode. The black and yellow cords are chilled water lines that cool the APDs. As a consequence, dry gases have to be added to keep the electronics from frosting over. After I saw the finishing touches that were added to the detector, it was time to step back and contemplate my lasting impression of the detector in general. Well, all I can say is that they have one massive detector.
Some of the numbers are just mind-boggling. To build this detector, we use 12,000 kilometers of fiber.
But of all those statistics, there were three things that really impressed me about the detector. First was its long length. Second was the height and width of the detector's face at one end. And lastly was the amount of instrumentation attached to the detector. Now that we have an understanding of the neutrino detector, let's find out about Fermilab, which is the source of the neutrinos.
So Fermilab is kind of northwest of Chicago by about an hour, and they've been there since the early 70s was when they started building the Fermilab accelerator, and only just a few years ago it was the most powerful accelerator in the world.
At Fermilab, the process of making neutrinos starts out by taking hydrogen atoms and removing their electrons with a magnet. This leaves behind only protons, which are then placed into an accelerator called the main injector. When the protons get up to speed and leave the circular-shaped main injector, the proton beam is bent downward to compensate for the Earth's curvature between Fermilab and NOvA. Once the beam trajectory is angled downward, then the protons proceed to a target made of carbon.
And once it hits the target area, which is this thing right here, which is basically just pure carbon, that's where the collision happens. And as we described before, it's just like hitting the billiard ball into your rack of balls. They just go in every direction. So that's not really what you want. So we have a horn that's right after the target. It actually runs about 250,000 amps power. It has massive power cables coming to this, and that focuses all those particles back into a beam size that's roughly the size of a pencil. The proton beam is smaller than a human hair when it first starts, and then this gets it back down to the size of a pencil, and then horn 2 focuses it back down again to even smaller, so it's about 1/8 of an inch by the time it comes out of the second horn, and then it goes through this long 675 meter decay pipe. And so most of the particles don't live that long, and they all decay off, and then you're left with basically a pure beam of muon neutrinos.
That beam of pure muon neutrinos then passes through one last mechanism at Fermilab. It's actually the first neutrino detector in this story, Fermilab's near detector. Once the muon neutrinos have passed through the near detector, they begin their long, but very brief, journey to northern Minnesota. What scientists are looking for are differences between what they see at the near detector and what they see at NOvA. For example, one of the differences that they expect to see is some of the muon neutrinos will oscillate into electron neutrinos. Another thing they might learn about is the hierarchy of mass between the three types of neutrinos. Although a primary focus of this program has been on the NOvA FAR detector at Ash River, the older MINOS detector at Sudan is still part of the same experiment, and MINOS will continue to operate at least through fiscal year 2015, and likely longer. It probably should be explained, however, that there are a couple of big differences between the NOvA and MINOS detectors.
The MINOS detector, which was one big difference between this detector, two big differences. One is it's a half a mile underground, so it gets rid of a lot of the cosmic ray background noise that we have to deal with here. And the other one is it's based out of steel instead of scintillator oil. So it's actually a big toroid magnet as well. So we can actually see the charge of the interaction when the particles interact, which we can't see in this detector.
However, compared to MINOS, the liquid scintillator at NOvA has an efficiency advantage. And by the way, think of a scintillator as a detection medium.
And so one of the big differences between the liquid scintillator detector and this one, most of the mass is steel. And so we only have a little tiny sampling, and then we have an inch of mass that we don't know what's happening. Where this one, it's roughly 70% liquid scintillator, which we're actually reading out. And so this detector, we have 70% active. This detector, we only have somewhere between 1 and 2% of the actual mass is active. And so you get a much cleaner snapshot of what's happening.
Fair enough. But Professor Habig did say that neutrinos are slippery. In other words, even an efficient detector won't detect a lot of neutrino interactions.
They only interact every once in a while. In fact, we only expect to see a couple of neutrino interactions from the accelerator every month of lifetime that we have. So that's why you have to build a very, very big detector.
Which leads to a couple questions. First of all, what is it about neutrinos that makes them, well, so slippery? In other words, so hard to detect?
Primarily because neutrinos are neutral. So, the opposites attract and likes repel, right, with magnet poles or with positive and negative charges. And so right now, you're sitting on this chair, and the atoms that compose you have nuclei, which are positive, and this cloud of electrons around them, which are negative, right, so from chemistry class. And the reason that you are sitting on the chair and not falling through it is because your electrons are negative and the chair's electrons on their atoms are negative, and you get too close and they repel. So you're sitting there. But an atom is mostly empty space, it turns out. The nucleus of an atom is something like 100,000th the size of a whole atom. Most of an atom is this cloud of diffuse electrons zipping about. And so if you were not charged, you wouldn't repel from the chair's electrons, and you would just go right through the chair's empty space, passing through your empty space, and you'd never know the difference. In fact, if you think of the solar system, most of the mass of the solar system is in the sun, 99% of it, right there in the middle of the solar system. And then there are a few planets out there, and it's mostly empty space. And there's great pictures you can see of Voyager taking a picture of the sun and a few tiny little dots, which are planets, right? Solar system is really empty. It's not so different than an atom, where an atom, most of the mass is in that nucleus, right there in the middle. And there's a few tiny electrons out there, and the ratio of empty space to stuff is about the same as our solar system.
A quick analogy here to illustrate Professor Habig's point. If this bead, which is the size of a pea, was the nucleus of an atom, and it was placed at the 50-yard line inside the Metrodome, then the nearest electrons would be buzzing around the upper ring of seats inside the Metrodome.
So when you think of that, if you're a neutral particle and you don't care if something is positive or negative, because you're not being repelled or attracted from either of them, you just go right through the empty space.